In today's video lecture, we are going to continue with the concepts of phasors and impedances in solving sinusoidal steady state problems. Let's start with this problem here. The circuit is the same circuit we saw in a previous example with a capacitor, an inductor, and a couple resistors. But in this question, we're asked to determine the frequency omega at which the current leaving the voltage source is in phase with the voltage. In the phasor domain then, we have our voltage phasor, our current phasor, an equivalent impedance, C equivalent, which from a previous example we saw was 4 plus 2 omega squared over 4 plus omega squared. That's the real part. And the imaginary part was J4 omega over 4 plus omega squared minus 2 over omega. For IS to be in phase with VS, we need the imaginary part, the reactance, must equal 0. Once again, for IS to be in phase with VS. So all we need to do is to set this part of the expression equal to 0 and solve for omega. Basically, we want 4 omega over 4 plus omega squared to equal 2 over omega. So we get 4 omega squared equals 8 plus 2 omega squared, or 2 omega squared equals 8. Omega squared is 4, or omega is 2 radians per second. And you can verify by plugging 2 into the expression above that Z equivalent is 4 plus 2 times 2 squared over 4 plus 2 squared plus J, 4 times 2 over 4 plus 2 squared minus 2 over 2. You get 5 plus J0 ohms. So the answer is if we are operating this circuit at a frequency of 2 radians per second, the current leaving the voltage source will be in phase with the voltage. In this problem, we're told that an inductor-resistor combination has an equivalent impedance given by Z equals 30 plus J40 ohms. And we're told that the operating frequency is 500 radians per second, and we want to determine the value of the inductor and the resistor, and we're going to look at two different situations. In the first situation, the resistor and inductor are going to be in series. So in series, if the impedance is 30 plus J40, and we have this situation here, that's just R plus J omega L. So we can immediately read off that the equivalent resistance is 30 ohms. We also know that omega times L has to be 40, but omega is 500 radians per second. So solving for L, you get 80 millihenries. So one solution would be a series combination of a 30 ohm resistor and an 80 millihenry inductor. But we could also achieve 30 plus J40 by doing a parallel combination of a resistor and an inductor. Here, however, because we're in parallel, it's probably easier to work with admittances. I mentioned earlier that we almost exclusively work with impedances rather than admittances, but there are a couple situations, and this is one of them, where doing everything with admittances is a little bit simpler. So if we know that Z equivalent is 30 plus J40, we're given that in the problem, that means that the corresponding admittance is 1 over 30 plus J40, which is equal to 30 minus J40 over 2500, which is equal to 3 over 250 minus J4 over 250. If you don't remember how we get to this point here, You get that by multiplying this expression here by the conjugate of the denominator over itself. Doing this makes the denominator totally real, and we get 3 over 250 minus j4 over 250. So to solve for R and L in this case, let's think about the equivalent admittance here. Y equivalent is just the admittance of that plus the admittance of that. The admittance of a resistor is just its conductance, so it's 1 over R. The admittance of an inductor is 1 over its impedance, or 1 over j omega L. Remember, admittances in parallel add. Of course, 1 over j omega L we can rewrite as minus j over omega L. And this is now in the form that we can now set this equal to this, and that equal to that. So we get 1 over R is 3 over 250. So the resistance in this case is 250 over 3 ohms. We also get the minus 1 over omega L equals minus 4 over 250. Solving for L, we get L equal to 250 over 4 omega, or 125 millihenry. So in this case, R is 250 over 3 ohms, and L is 125 millihenry. So now that we've done a couple examples dealing with impedances and admittances in sinusoidal steady state, let's think about solving circuits in general when we have a sinusoidal steady state input. So the algorithm for doing sinusoidal steady state analysis is actually very simple. The first step is you redraw the circuit or redraw the network using the following things. Wherever you see a sinusoidal source, replace it by a phasor. Whenever you have a sinusoidal variable, a voltage variable, a current variable, replace it by a phasor variable. And wherever you see inductors and capacitors, replace them by their corresponding impedances. At this point, we now have an equivalent circuit in what we call the phasor domain. The only difference is we have phasor voltage and currents and impedances instead of capacitors and inductors. At this point, the second step now is we can solve the circuit using any techniques that we've learned before. So we can use KVL, KCL, nodal analysis, mesh analysis, Thevenin's theorem, linearity, superposition, source transformations, you name it. We could use any techniques we used with purely resistive circuits, except now all of our math is going to be in complex numbers. Once we're done with that, we end up with a complex number phasor for whatever voltage or current we're looking for. Some XM at an angle of phi. All you need to do then for the last step is convert it back into the time domain by setting the magnitude of that complex number equal to the magnitude of the sinusoid, set the phase of the complex number equal to the phase of the sinusoid, and then our operating frequency you just stick back here. Let's look at another example. In this example, we're given a circuit with a capacitor, an inductor, a couple resistors, and a sinusoidal voltage source, and we're asked to find the sinusoidal steady state current, Is of t. The way to solve this is to find the phasor domain equivalent of this circuit and then solve it. The phasor domain, the voltage source just becomes a voltage phasor, 169.7 at an angle of 0 degrees volts. The current we're solving for is now going to be a phasor variable. And every component now you replace by its impedance equivalent. Resistors, there's really nothing you need to do with. A capacitor is minus j over omega c, since omega is 2 pi times 60. that's 377 radians per second. This becomes minus J 2.653 ohms. The inductor, J omega L, becomes J 3.77 ohms. And of course, resistors, once again, are unchanged. So this is the equivalent circuit. And how would you solve for IS in this case? Well, there are a couple approaches. You could use mesh analysis with two meshes, a mesh on the left, a mesh on the right. You could use nodal analysis with two different node voltages and solve for them. But probably the easiest thing here is to just find Z equivalent and then set IS tilde equal to VS tilde over Z equivalent. So doing this approach, IS tilde is going to be 169.7 at an angle of 0 volts over, so what is the equivalent impedance? You have these two are in series. Those are then in parallel with that, and that combination is then in series with that. So writing it down, we get 2 is in series with J 3.77. That combination is now in parallel with minus J 2.653, and that combination is then in series with 1. So this parallel combination is a product over the sum, 2 plus J 3.77 times minus J 2.653 all over 2 plus J 3.77 minus J 2.653, the product over the sum. You work out the math, you would get 2.68 minus J 4.15 ohms. You then add it to 1 and you get 3.68 minus J 4.15 ohms. Of course, the numerator is 169.7 at an angle of 0 volts. You can either calculate this on your calculator directly, or if your calculator does not do complex numbers, you need to convert the denominator to its polar form. It's 5.55 at an angle of minus 48.4 degrees. Then you divide the magnitudes and subtract the angles. 169.7 divided by 5.55 is 30.58. 0 degrees minus negative 48.4 degrees is 48.4 degrees. And of course the answer is amps. We finally convert this back to the time domain to get IS of t is 30.58 cosine. And now we plug back in the frequency of operation, 2 pi times 60, or 377 t plus 48.4 degrees amps. Suppose we were asked to also find the current IC. The way we could find that is using current division. So if we were asked to find IC tilde then is what? It's IS tilde times the opposite impedance over the sum of the two impedances. So once again, this current is equal to this current times this impedance over the sum of that impedance plus that impedance. So IC we could express as the opposite impedance, 2 plus J 3.77, over the sum of the two, 2 plus J 3.77, minus J 2.653. All of that times this IS phasor that we solved for already. It's current division in the phasor domain. Notice that this 1 ohm resistor here does not show up in this equation on the right here because we know IS already. You work out the math. This becomes IS phasor times 1.86 and an angle of 32.9 degrees. And IS, of course, was 30.68 at an angle of 48.4. You work out that math, you get 56.88 at an angle of 81.3 degrees amps. So we could write our second equation here, IC of t, is 56.88 cosine of 377t plus 81.3 degrees amps. If after that you wanted the voltage across the capacitor, you could do that a couple different ways. One way you could do it is multiply IC phasor by this impedance. Remember, voltage is current times impedance. The other thing you could do is you could recognize the fact that the voltage across the capacitor is 1 over C times the integral of the current. So you could actually find VC of t a couple different ways. So let's do another example. In this example, we're going to use mesh analysis to solve for the current I in this rightmost loop. So once again, because this is a sinusoidal steady state analysis problem, we're going to redraw the circuit in its phasor domain. Let's start with the current source. 10 cosine 10 to the 4th t in the time domain. In the phasor domain is just 10 at an angle of 0 amps. The inductor on the left, the 1 millihenry inductor, becomes J omega L. Omega is 10 to the 4th radians per second. Multiply that by 1 millihenry, we get J10 ohms. The capacitor, minus J over omega C. Since you have 2 microfarads and 10 to the 4th radians per second, this becomes minus J50 ohms. This inductor here, 4 millihenry times 10 to the 4th becomes 40, so this becomes a J40 ohm resistor. And the resistor just stays the same. How about the dependent source? Well, because it's a source, we're going to use phasors. The only difference is now instead of 3Vx, it's 3Vx phasor, and we need to define Vx phasor. Vx phasor is the voltage across this current source. So Vx phasor is given by that. So let's use mesh analysis to solve for this circuit. Our mesh variables are going to be I1 phasor, which is the current in this left loop, I2 phasor, which is what we're ultimately looking for, is going to be the current in the rightmost loop. So using mesh analysis, what would we do? Well, we would notice that because we have this interior current source, we need to use a supermesh. So our supermesh KVL equation is what? Starting down here, we get J10 times I1 tilde minus J50 times I2 tilde plus J40 times I2 tilde plus 20 times I2 tilde minus 3Vx tilde is equal to 0. But remember, when we do nodal and mesh analysis, we need to get rid of these control variables if it's not one of the variables that we want to end up with. So we notice that Vx, which is the voltage across the current source, it's also the voltage across the 1 millihenry inductor on the left, and we see that Vx tilde is nothing more than negative J10 times I1 tilde. Why is it negative? Because I1 is going in this direction through the inductor, and so from the passive sign convention, the voltage across this inductor would be I1 times J10 with the plus here and the minus there. Since Vx is defined with the plus here and the minus there, we need a minus sign. So Vx is minus J10 times I1. To simplify the equation, let's look at all the terms that have the I1 tilde in them. That's this one and this one. And we see that we get J30 plus J10 all multiplied by I1. So we get J40 times I1 tilde. And then the terms with the I2 are that one, and that one. And that becomes 20 minus J10 multiplied by I2 is equal to 0. So that is our super mesh KVL equation. We also need a source equation. The source equation is what? We know that IS, which is 10 at an angle of 0 amps, is equal to that current minus that current. So that's just I2 tilde minus I1 tilde. Or I1 tilde is equal to I2 tilde minus 10 at an angle of 0 degrees amps. So what we want to do is plug this into here and solve for I2 tilde. We'll do that on the next page. So what do we have? We have J40 times I1 tilde, which is I2 tilde minus 10, plus 20 minus J10 times I2 tilde is equal to 0. The only unknown left in this equation is I2 tilde. So we get I2 tilde times 20 plus J30 is equal to J400, or I2 tilde is J400, which is 400 at an angle of 90 degrees, over 20 plus J30, which is 36.06 at an angle of 56.3 degrees. You work out that math, it's 11.09 at an angle of 33.7 degrees. So I2 of t, which is what we're ultimately looking for, is just 11.09 cosine 10 to the 4th t plus 33.7 degrees amps. To show that there are multiple ways to solve almost every problem, let's solve the same problem using another approach. Rather than doing mesh analysis, let's convert this current source and parallel impedance to a voltage source and a series impedance. In other words, we're going to do a source transformation that is going to give us a single loop circuit, and we can then solve that single loop circuit to find the current I2, and we should see that we get the exact same result. So now we're looking at this alternate way to solve. So the idea here is we're going to take this parallel combination of a current source and a parallel impedance and replace it by a voltage source and a series impedance. The voltage source is what? It's going to be 10 at an angle of 0 times J10. So this is going to be 10 at an angle of 0 times J10. and we get 100 at an angle of 90 degrees volts. And the series impedance is the same as the parallel impedance. When you do a source transformation, whatever impedance you have here shows up there. Now we can stick that back into the original circuit. So we still had our minus J50, we still had our J40, we still had our 20, we still had our dependent source, minus plus 3 Vx tilde, and Vx tilde is that voltage there. And this current is still our current I that we're looking for. The idea behind this source transformation, though, using that instead of this, is we now have a single loop that we can work with. So the first thing we need to do to find I tilde is we want to get rid of Vx tilde. Vx tilde is the voltage at this point here. It's going to be this voltage minus the voltage drop across that J10 impedance. The voltage drop across that impedance is going to be just J10 times I tilde. So we get that Vx tilde is 100 at an angle of 90 degrees minus J10 times I tilde. So now we can do KVL starting from this point. We get minus 100 at 90 degrees plus J10 times I tilde minus J50 times I tilde plus J40 times I tilde plus 20 times I tilde minus 3 times Vx, which was 100 at an angle of 90 degrees, minus J10 times I tilde, all of that equal to 0. If you work out the math and solve for I tilde, you will get I tilde is the same answer we got before. So once again, I'm just illustrating here that you could solve a circuit using many different approaches. I'm not going to do it here, but you could solve this circuit using nodal analysis if you wanted to. It'd be a lot of work though, because you have a voltage there, a voltage there, a voltage there, a voltage there. You end up getting many more equations than you need to solve the circuit. So just like in a resistive case, in a sinusoidal steady state case, you will find that some methods are going to be easier than other methods. In this example, either source transformations or mesh analysis would be good choices. In this example, we're given a relatively easy circuit, but we're asked to find the Thevenin equivalent for this network if the voltage source is 50 sine 1000 t volts. The way you would solve this is just like you would solve a resistive Thevenin problem. You find VOC and you find Z Thevenin. So let's find VOC, and this is going to be a phasor VOC. So the voltage source, 50 sine 1000 t, because this is a sine, this is going to be 50 at an angle of minus 90 degrees. $80 ohm resistor has an impedance of 80 ohms still. A 0.2 Henry inductor, its impedance is J omega L. So it's going to be J times 1000 times 0.2, or J 200 ohms. So VOC tilde is that, and we can use voltage division. VOC tilde is J200 over J200 plus 80 times 50 at an angle of minus 90 degrees. So J200 over J200 plus 80 times 50 at an angle of minus 90 degrees. You work out the math, you get 46.4 at an angle of minus 68.2 degrees volts. Then instead of finding R Thevenin, we find Z Thevenin. How do you find Z Thevenin? The same way you would find R Thevenin. You set the voltage source equal to 0. We have our two impedances here, and we're finding the equivalent impedance looking into these terminals. And it's just going to be 80 ohms in parallel with J200 ohms. And what's that? It's the product over the sum. 80 times J200 is 16,000 at an angle of 90 degrees. And 80 plus J200 is just 215.4 at an angle of 68.2 degrees. You work out this math, you get 74.28 at an angle of 21.8 degrees ohms. Impedances you almost always like to express in rectangular coordinates, so this would be 68.97 plus J 27.58 ohms. So we can now draw the Thevenin equivalent circuit in both the phasor domain and then in the time domain. In the phasor domain, we have a phasor voltage of 46.4 at an angle of minus 68.2 degrees volts. And we have Z Thevenin, 68.97 plus J, 27.58 ohms. In the time domain, the voltage source becomes 46.4 cosine of 1000 T minus 68.2 degrees volts. How about the impedance? Because we have a plus here, this means the equivalent impedance should be a resistance and an inductance. So the resistor value would just be 68.97 ohms. The inductor value, remembering that J omega L has to equal J 27.58, we get L is 27.58 divided by omega, which is 1000, or 27.58 millihenry. So we see that at an operating frequency of 1000 radians per second, we get this Thevenin equivalent of the circuit. An important thing to point out is Thevenin equivalents are frequency dependent. So this is the Thevenin equivalent. Only at an operating frequency of 1000 radians per second. So we've done a number of examples here. We used Thevenin's theorem, we did mesh analysis, we did current division, we did voltage division of place, we did a source transformation, and what we're seeing is all of these different circuit analysis techniques that we used earlier, we can use again now in sinusoidal steady state analysis. The only wrinkle is that we have complex numbers, so it's important that you're adept at using complex numbers on your calculator so that you can do these calculations relatively quickly. Next class, we're going to look at what happens if you have inputs of different frequencies, because in reality, you're typically not going to have inputs of just one frequency, 1,000 radians per second, 100 radians per second, 60 hertz. You're going to have inputs of multiple frequencies. So what do you do in situations like that? We're going to see that you have to use superposition. So we'll pick that up next class. Anyway, have a good day.